Thank you very much for the kind introduction, and not least for inviting the Bellona Foundation to come here and talk about a topic which is, I would say, very close to our heart, having fought for more than 25 years to protect marine environments, and particularly in the Arctic. But unfortunately, that's not what I've been invited here to talk about today. But I would like to say a few words about our organization nonetheless. Bellona is a science-based environmental NGO, which has offices, the head office is in Oslo, but we also have offices in Washington, and as you can see, also 2 offices in Russia, one in St. Petersburg and one in Murmansk, which also emphasizes the focus we have on Arctic areas. And the EU policy and advocacy office in Brussels, which I'm currently heading. Now, the topic I'm going to talk about today is very much connected to the overarching issue of climate change, which we have been working on very much for the last decades, and which is now also becoming ever more urgent. Obviously, global warming and climate change, and this scenario on how to combat warming was something that Bellona was producing back in 2008 as a follow-up to the IPCC fourth assessment report, showing that we have to cut at least 85% of global emissions by 2050 in order to stop disastrous climate change from happening. So the thing which might stick out here compared to many other scenarios that you might have seen for dealing with climate change is that we found that using technologies which exist today, or of course this was in 2008, we might need to do some slight changes now, but from what we saw then was that CCS, carbon capture and storage, is going to have a very crucial role. And the role is not only connected to capturing emissions from fossil fuel power plants, which is the general connection you see with CCS, especially for coal, but also for gas. But it's even more connected to combining CCS with bioenergy in the various forms. And I'll get a bit back to that, but I just wanted to show you this scenario first to show the enormous impact that CCS can have on stopping climate change if it's applied in the correct way. So Bellona was actually the first environmental NGO to put CCS, carbon capture and storage, on the policy agenda in Norway back in the early 90s, when this was by most people seen as a utopia and a quite crazy idea to take that CO2 from a power plant and put it underground. But about 10 years later, Bellona was one of the co-founders of the Zero Emission platform, the European technology platform for CCS, for power plants, which today unites more than 300 members from the science community, from the industry, and from the civil society to enable CCS to be developed and deployed in time to actually deal with the climate issue. And because of what we saw, that CCS has to be combined with biofuels and bioenergy, we also decided to join the steering committee of the European Biofuels Technology Platform in order to bring people working with bioenergy and biofuels together with those who are experts on CCS. And that, I would say, had not been talking much together before this. So just to explain the concept briefly, this is a very simplistic figure, but to the left you see energy produced from fossil fuels. You take fossil carbon up from underground, you convert it to energy, and the carbon is released as CO2 into the atmosphere. Now, the next figure is with CCS deployed for this kind of energy production, where most of that carbon is put back into the ground and stored permanently. But some of it is still going up because the capture technologies cannot capture all of it. Then the next one is what we define as carbon neutral. It's of course not a perfect definition, but that's the definition it's used today for renewable energies as well as nuclear energy, and bioenergy should also be mentioned here. There are many who question the sustainability of bioenergy, but it should be in this definition system, given that the biomass supply is sustainable, also carbon neutral. Now, if you take the CO2, which is converted the CO2 which is released when you convert biomass into fuels or energy, and you capture that CO2, and you ensure that the new biomass is grown to replace the one that was used for this conversion, you actually take CO2 out of the atmosphere over time. And this is the concept of carbon negative, which I wanted to talk a bit about today. Because last year, the UNFCCC was warning that we are completely missing the targets for dealing with climate change, and we will have to develop stronger technologies to actually remove CO2 out of the atmosphere in the future. And we were hearing a bit here now from Stephen about biological systems, but they will not be able to do this job alone, and therefore the only current technology option for actually removing CO2 on a large scale out of the atmosphere is combining sustainable bioenergy with CCS. So based on our warning, we initiated this joint task force between the two technology platforms on European level to look into how this can be done in practice. And in June this year, the two platforms produced or published this report called Biomass with CO2 Capture and Storage. I have a few more copies with me, but not many, so it can also be found on the websites of the two platforms for those who are interested. I just wanted to say a little bit about what came out of that report and that work which has been going on for the last 2 years within those platforms. We also had members such as the IEA, for example, taking part in this work. And it's been a long way to go to actually bring people from the power community, the CCS community, to actually come up with some common understanding with those who are working for bioenergy and renewable energy. So the report shows the 4 main conversion routes that we have today to actually combine biomass and CCS. The first one is perhaps the most obvious, where you co-fire, meaning you put a percentage of biomass to replace coal or gas in a existing power plant, and then when you apply CCS to this power plant, you can actually go into carbon negative, meaning if you capture, let's say, 95% of emissions from a coal-fired power plant, and you fire 20% biomass to replace that coal, you will have 50% negative emissions if that biomass is sustainable. There are various routes to do that. I don't have time to go into details on this today. But the perhaps more interesting topic for today is the routes to produce biofuels, which is also a market which is growing very strongly. And one of those routes is fermentation of biomass into fuels, where CO2 is released during that fermentation at almost a pure stream of CO2. And that CO2 can be very easily captured and stored without expensive capture technology which you would need for a power plant. And that also makes it very interesting. But it's not being done today in Europe because there is no incentive for dealing with emissions that are not accounted for, such as emissions coming from biofuels production. It's seen as neutral, so no incentive for doing anything about it. Now, then you also have the thermic conversion routes where you gasify biomass, which in some ways can be seen as better because it uses the entire biomass, all the carbon in the biomass, to produce synthetic gas, which then can be changed into fuels and also other chemical products. And during the conversion product, you also have a pure stream of CO2, or near pure stream, that can be captured at a very low cost if this is incentivized. And finally, you also have a lot of industries like the steel industry, the cement industry, and so on that use today mainly coal to fuel their processes, but potentially also could change into using biomass instead. So, briefly about the conclusions of the report. The first one being that bio-CCS has to be an important part of the solution for climate change, and it's the only large-scale technology, as I mentioned, that can remove CO2 from the atmosphere over time. Secondly, as also mentioned, the costs for some of the biofuels production routes and capturing that CO2 are extremely low. And we also see that in the US already this is being done at an industrial scale. The first CCS project to be receiving funding from the Department of Energy in the US was actually a biofuels production site, which will capture 1 million tons of CO2 a year. And the reason for this is that it was much cheaper than any other CCS project. And we were looking into the technical potential using projections, moderate projections for sustainable biomass availability in Europe 2050. We saw that the annual potential for removing CO2 is actually around 800 million tons per year. Now, the problem with this is, of course, that the sustainability of biomass is being questioned for good reasons. And already today, with the 2020 targets for renewable energies in Europe, we see that more than 50% of the renewable energy in Europe, according to the national action plans for 2020, is going to be biomass, bioelectricity, biofuels, and bioheat. And we already see that Europe is not able to provide sustainable biomass domestically for this. And there's a lot of reasons for this, including logistics, including land use that is not very sensible today. But that brings us to the broader issue of biomass supply. And this is a number of macroeconomic trends which are quite dramatic, which we will see in the next decades. The population growth, which you all have heard that we're going to pass 9 billion people by 2050, is increasing the need for food, for cereals, for water, and at the same time you have the energy consumption going up, which leads to increase in CO2 emissions, which leads to climate change, which leads to an increase in arid areas. And this means that what we can derive from this is one thing: we're going to need a lot more biomass. And the problem with current biofuels production, for example, is that it competes with food production. And we see that this is not possible when we're going to need so much more food. And that brings us back to today's setting, because there is one type of biomass which does not compete with food production, that's algae. And algae is growing extremely quick compared to many other biomass types. It also has positive effects on the acidification of the oceans, and that's why we started working with algae. And I would just like to put this into relation with the report, because today there's still a lot of problems with thermic conversion of algae due to the high salt and water levels. But we have quite a few successful projects, both underway and some that have been finished, on fermentation of algae into biofuels, where CO2 is released and where therefore CO2 could be captured, and you can create a carbon negative system with using algae. So it's possible. We have also a lot of research going on how to use algae for co-firing in power plants, but there are a lot of challenges, especially because of the salt levels that create corrosion in power plants. But anyway, the need for this additional power plant is something that led Bellona to start working with scientists, mainly in Norway, to look into how we can produce more seaweed, how we can create huge farms to produce this additional biomass that we're going to need. And I was very happy to hear Professor just presenting also a concept that we're integrating seaweed production with seafood production with, for example, other types of energy production. Because this is the kind of concepts that we're very fond of in Bellona, integrating various energy systems and bringing scientists together from and also with industry from various backgrounds. So we see also here we have a project which is using excess nutrition from fish farms outside the Norwegian Sea, where we have a lot of fish farms which are using enormous amounts of nutrients, which is not sustainable in terms of food production. But if these excess nutrients could be used to produce, for example, other seafood and seaweed for energy production, you would have a much more sustainable system. And we see that the potential for using those nutrients is actually very large. We have a project together with the Norwegian Research Institute, SINTEF, and the Norwegian University of Technology, which going until 2015 to look into the actual potential of doing this outside the shores of Norway. And I would just like to end with a few slides showing the vision that we have for this kind of integration. Obviously, you have the wind farms, which mentioned already. And you could then add the nutritions from the bottom of the sea, which are already there, to be pumped up into seaweed production, along with excess nutritions from the seafood farms. And then you could also add microalgae production, which takes even less space and which has an even higher energy content than most seaweed. In an integrating system, subsea turbines is another alternative to the onshore turbines that, or for wind. We can also produce energy undersea with the wave energy, and finally, there's a potential to integrate solar energy in this. So we would like to see more of those kind of projects where people are brought together from different industries and science communities to look into how you can combine it. It's very good to see that other people are doing the same. I think that was all for me. So thank you very much for the attention.